Hello and welcome to my presentation for the Engineering Design Show. I am Jacob Pemberton and will be presenting my work on a supercapacitor based nail gun. This presentation will be presented in a form reflecting a poster commonly seen at a design show. I will be exploring the design and development of a supercapacitor based nail gun. Nail guns are an incredibly popular device often found at construction sites or at the home of renovators or woodworkers. Traditionally, nail guns were pneumatic. However, they are cumbersome due to the attached compressor and nozzle. Eventually, through demand and innovation, they've started being replaced by electric guns. Initially, they were just corded models, which didn't show much of an improvement over pneumatic. But eventually, an age of batteries entered the world of power tools. While highly regarded for their maneuverability, they're heavy and are often regarded as being underpowered. Innovation may be presenting itself again, this time in the form of supercapacitors. Supercapacitors are a relatively new player in the field of electrical energy storage. They can provide high power output while still having a reasonably high energy storage. So how does one go about finding how viable supercapacitors are as an energy source for nail guns? Well, an understanding of how current electric nail guns operate is a good start. Understanding how the firing mechanism operates, the significance of the control circuit, and what sort of voltages are typically used. These factors are explored and analysed later in this presentation and have been changed as needed to meet the needs of a supercapacitor. Once a fully operational prototype has been developed and tested, it will need to be compared to the original battery model to find how effective the supercapacitor model is. Figure 5 shows an Waikato SNL1000. This model was chosen for its low voltage, low power, and low price. The first two reasons are significant as not only did it increase safety, but the low voltage also means that the low voltage rating of supercapacitors will make for an easier comparison. Various components of the nail gun have been shown for understanding. Component 1 of the nail gun shows the control unit. This is the brain behind the power. It ensures that the nail gun fires when it is meant to, informs the user of the charge of the battery, and controls the charging of the battery. Component 2 is the battery itself. It is a 3.6 volt, 1.5 amp hour lithium ion battery. Component 3 is the motor. It is a 6 volt brushless DC motor. The final component is the spring and associated housing. The nail gun works by first ensuring the gun is pressed against the material. This is done by a simple switch connected to the base of the gun. Next, the trigger is pressed, and assuming there is sufficient charge in the battery, a MOSFET will then be activated, causing a voltage across the motor. This voltage is less than that of the output of the battery. This is due to an onboard voltage regulation. As the motor turns, an arm catches the spring, resulting in the spring compressing. Once the motor arm no longer has contact with the spring, a switch is pressed. This informs the control board that the motor has completed its full rotation and thus a nail has been fired. Testing began with observing the battery and motor during normal operation. This was done by observing the nail gun deplete a full charge by firing near continuously. To simulate real-world situations, the nail gun was fired in short 10-shot bursts with a 1-minute break. This reflects a user who would pick up and use the nail gun, then move around, reposition themselves, and continue using the nail gun. The results of this showed that the nail gun operates in a voltage range between 4.05 and 3.63 volts. The nail gun was able to fire 716 nails in the method described. The results are shown here in Figure 6. This test gave important data to consider for selecting the supercapacitors for the bank. Given that supercapacitors have a maximum voltage less than the minimum voltage recorded in the test, it is evident that two capacitors in series are going to be needed. When applying supercapacitors in series, the capacitance decreases. For two capacitors of the same value, this results in half the total capacitance. Another factor to consider for selecting capacitors is the volumetric size. It must be able to fit inside a gun similar to the size of the Waikato SNL1000. This will allow for a fair comparison. When examining the board, voltage regulation was observed as the voltage across the motor was different to that of the battery. Though testing showed that it was minimal, as observations from the two ends of the battery charge showed that the motor voltage change larger than expected. Considering this, a new circuit would need to be designed. To ensure accurate comparison, the same motor and spring were used. When testing the circuit for the supercapacitor nail gun, initial results showed that a 20 mV per 10 nails drop occurred on the supercapacitor. This is compared to 5.9 mV average per 10 nails for the battery. While this does show a worse result, this value is expected to decrease as testing continues. However, shortly after testing began, the microcontroller became unresponsive. This prevented further testing as this occurred during lockdown and a replacement microcontroller could not be obtained. Due to the fact that minimal data has been obtained, a conclusion to the viability of a nail gun cannot be fully examined. The limited test data did show that the nail gun is able to function, though the extent to which it's able to last is the important factor that needs to be further explored. It is known that supercapacitors are able to fully discharge as opposed to batteries which have a limited discharge curve. This concludes my presentation. I hope you enjoyed and thank you for listening.